All right, so our final intermolecular force is known as hydrogen bonding. And although it's called hydrogen bonding, it's not actually a bond, it's just a type of intermolecular force. So it's called hydrogen bonding, but it's not actually a bond. And really, it's just an extension of a dipole-dipole interaction. It's not too different than a dipole-dipole interaction. And even though it's called a hydrogen bond, it's still an intermolecular force, and so it's still weaker than a regular bond. And so what is it? So hydrogen bonding is a dipole-dipole interaction between HF molecules, HF-containing molecules, NH-containing molecules, or OH-containing molecules, right? So if they contain one of these bonds, then the molecule can participate in hydrogen bonding. Why nitrogen, oxygen, and fluorine? Well, they're the most electronegative elements, and so they induce the biggest dipole. And so this is just essentially an extreme version of a dipole-dipole interaction, right? So there's a large electronegativity difference here. And so the reason we pay attention to it so much is that we live in a world that's mostly water. We are mostly water, and water has an OH bond, so it participates in hydrogen bonding. So it's very important for life, and so that's why it gets this special name. So if we think about OH here, right, there's some water there, and if we think about another molecule of water, right, the interaction here, so right, there's dipoles here, and the interaction between this lone pair and an adjacent hydrogen is what a hydrogen bond is, right? So there's your hydrogen bonding, and it can occur between HF, NH, or OH containing molecules. Here's just another picture of it right here. They don't explicitly show the lone pairs, but they are there, right? There are lone pairs here, which are bonding to these other compounds. And hydrogen bonding, or water, can actually participate in two hydrogen bonds, right? So you can have this lone pair attacking another hydrogen, or you can have this other lone pair being attracted to another hydrogen on a separate water. So it actually has two sources of hydrogen bonding. So let's take a look at an example of this. So here we have ethanol on the left. So this is the alcohol that you drink. Right, and we see that it contains an OH in it, right? An OH, so it will be capable of hydrogen bonding. And then we think about diethyl ether. Right, and so they have the same chemical formula, but this one does not have a hydrogen bond, right? It has an oxygen, but the oxygen is not connected to a hydrogen bond. And so if you think about what the boiling points are going to be here, the boiling point for ethanol, which has hydrogen bonding, which I think I forgot to mention is the strongest IMF, right? It has hydrogen bonding, so it will have a very high boiling point of 78.3 degrees Celsius, while diethyl ether, the same mass, has a boiling point of negative 22.0 degrees Celsius because it does not have hydrogen bonding, which is the strongest intermolecular force there is. All right, so let's do a little exercise. So place in order of increasing boiling point, right? So increasing boiling point with H2S, H2O, H2SE, and then H2TE. So go ahead, pause the video and place these in order of increasing boiling point. All right, so hopefully you paused the video. So let's take a look at the periodic table. We can see that this H part is all the same. So really, we're trying to think about the differences between sulfur, oxygen, selenium, and tellurium. And so if we take a look at the periodic table, we see that they're all in the same group, right? So they're all in the same column. And we remember our London dispersion forces. As we get bigger, we increase boiling point, right? So TE is the biggest, while water is the smallest. And then I guess selenium is second biggest. And then this one, I guess, is third biggest. Right, so you might expect to have H2TE to have the highest boiling point, but we just learned that this OH bond can participate in hydrogen bonding. And so it will actually have the highest boiling point. So H2O will have the highest boiling point. These other three components cannot participate in hydrogen bonding. And so after water, then you just go from biggest to smallest because of London dispersion forces. So then you have H2TE, H2SE, and then H2S, right? So that's what this figure here shows. And you can see it follows the same trend with HF and other halogens, and then NH3 and other pnictogens. So you can see as we get smaller, our boiling point decreases, and then it skyrockets up when we include a molecule that is capable of hydrogen bonding. So just a little fun fact for you here. Hydrogen bonding is how your DNA stays together. So maybe in biology, you learned that DNA is made out of two strands that are stuck together, right? But they can be kind of torn apart to replicate and make some enzymes and whatnot. But how do they stick together? Why do they stick together? Why do they match the way they do? And it's all due to hydrogen bonding, right? So you can see in this left here, it's making new strands of DNA, and you can see these little dots. These little dots are indicative of these hydrogen bonds between the different DNA bases. So you can see the AT only has 2 hydrogen bonds, the GC has 3, and so they match up to pair with one another, but not, T to G and whatnot. But that's kind of more biology. Just a little fun fact for you.